Okay, math people, we're here talking about section 3.2, so this is part 1 for that particular section. This is the very bottom of page 3 of your chapter 3 notes. We're proving lines parallel. So what we're going to do in this section here is the exact opposite of what we did in the previous section. In section 3.1 we said if you know the lines are parallel, now you know certain things about angles. Maybe the angles are congruent, maybe the angles are supplementary. This section here says we're going to use the fact that we know corresponding angles are equal, or we know alternate interior angles are equal. And we're going to use that fact to show, well, then the lines must be parallel. So it's going to switch the beginning and the end of these theorems. It's going to switch the converse, hypothesis with the conclusion. So basically what we're going to be doing is writing a bunch of converses here. Start off with the corresponding angles postulate, and now we're going to do the converse of that. So it says, if you know that the corresponding angles are congruent, which is what we're going to put right there, then you know the two lines must be parallel. You see in our diagram over here, you can see that they have corresponding angles of 1 and 2, and they're equal because they have the little arcs there. So because they're in the right location to be corresponding angles, we can now say that line L is parallel to line M. You notice here we don't have little arrows showing that lines L and M are parallel because we're starting off by not knowing that. We're using that as that's our conclusion. So we start off knowing something about the angles. Now we can say something about the lines. So as soon as you know corresponding angles match, guarantee the lines have to be parallel. Turning the page. Very similar idea here with the converse of the alternate interior angles theorem. We're going to use this diagram for theorem 3.5 and 3.6. And the first one talks about alternate interior angles. It says, if you know the two lines form alternate interior angles that are congruent, then you're allowed to make the conclusion that the lines must be parallel. Very similar to the previous postulate right there. So down here, you have 1, 2, and 4. The alternate interior angles are 1 and 2. So we're going to say if angle 1 is congruent to angle 2, then line L must be parallel to line M. So our hypothesis, or our starting point, is knowing something about the angles, and our conclusion, or the end point, means we now know something about the lines. And we don't have marks showing 2 and 1 being congruent here because we're also using this diagram for the next theorem as well. So that's why it's a little different. All right, the next one talks about the same side interior angles. And you remember the same side interior angles are not one of the pairs that are congruent, they're one of the pairs that are supplementary. So this theorem is going to say, if two lines form same side interior angles that are supplementary, then the two lines have to be parallel. In our diagram, 2 and 4 are the same side interior angles. So we're going to say if the measure of angle 2 plus the measure of angle 4 equals 180, then you're allowed to say that L is parallel to M. So if corresponding angles are equal, you can say the lines are parallel. If alternate interior angles are equal, you can say the lines are parallel. Or if you can prove that the same side interior angles are supplementary, you can also say that the lines are parallel. So example 1 here wants us to prove theorem 3.5, the converse of the alternate interior angles theorem. So we're going to start off by knowing that alternate interior angles are equal, and you see our little arcs over here. And we're going to end up by saying, well, then the lines must be parallel. So we said before that our given has to come from the symbols over here in the diagram or from the hypothesis up here. The hypothesis talks about the alternate interior angles being congruent. And you can see the arcs here. So that Both of those ideas tell us that our given should be 1 is congruent to 2, either because of the marks in the diagram or from the hypothesis of that statement. Proof always comes from the directions, or if it's written in the form of if-then like this one is, the proof has to come from the conclusion, or the end of the sentence. We're supposed to show that the lines are parallel. So we're trying to show that L is parallel to M. So here's where we're going to start, and there's where we're going to end up. So as usual, we're going to start off by stating what we know. We know that 1 is congruent to angle 2 because that is given to us. And we're going to keep working here until the very last thing we write on the left is going to be L is parallel to M. So we look at our numbers here. We have 1, 2, and 3. So those are the angles that we need to use or focus on. You see angle 3 here we haven't mentioned at all, so it has to be important in our proof. And you look at 3 relates to 1 because they are a pair of vertical angles. And we know from a previous theorem that vertical angles have to be equal. So we're going to say that angle 1 is congruent to angle 3. And we know that because of the vertical angles theorem. That's the theorem that says vertical angles are congruent. You can either write the name or the actual theorem. Right, so we're working here. We're trying to show that L is parallel to M. You look at what we have built up here. 1 is congruent to 2 and 1 is congruent to 3. Well, if both of these angles are congruent to 1, then they have to be equal to each other. There's no other way. So we know that angle 2 has to be congruent to angle 3. And for a reason, we can use one of two things. We can say it's a substitution property, because we're getting rid of angle 1 and replacing it with something we know is equal to angle 1. Or you can use the transitive property, because if 2 is equal to 1 and 1 is equal to 3, that means 2 has to equal 3. So as long as you have one of these properties, that's perfectly fine. You'll never have to have them both in the same line. It's either the substitution property or the transitive property. Right, so we're trying to show that L is parallel to M, and we're using we're trying to prove the converse of the alternate interior angles theorem. We can use any theorem or postulate that came before that, right? And the postulate that came right before that theorem said that if you know that corresponding angles are equal, the lines have to be parallel. Well, if you look at our diagram here, we just showed that 2 is equal to 3, and 2 and 3 are a pair of corresponding angles. So we just showed that corresponding angles are congruent, so now we're allowed to say that the lines have got to be parallel. And what idea did we just use there? That was the converse of the corresponding angles postulate. And yes, you need to say converse there, because the corresponding angles postulate is not the same as the converse here. We used the converse because we started by knowing that the corresponding angles are equal, and we concluded by saying the lines must be parallel, and that's what the converse says. The regular postulate without the converse says the exact opposite, but we went from here to there, so we used the converse. If we started by knowing the lines are parallel, and then concluded the corresponding angles have to be congruent, then we would have used just the plain old corresponding angles postulate. But here we used the converse. So we look back here, we start off by saying that alternate interior angles are congruent, and we kept working until we said then the lines must be parallel. So we just proved the converse of the alternate interior angles theorem. Moving on to example 2 at the bottom of the page. It says which lines, if any, must be parallel if 3 is going to be congruent to 4. So if you're trying to prove or trying to show to someone that 3 has to be equal to 4, which lines would you be interested in? Well, it comes back to the idea, kind of like the homework problem we had the other day. Which 3 of these lines do you need to build angles 3 and angles 4? Because there are 4 lines here, and one of them is not necessary. Well, if it helps you, you can just go ahead and redraw the 3 lines that are needed for 3 and 4. Because angle 3 sits right here, and angle 4 sits right there. And now that's a much simpler diagram to look at than this, and you can tell that these 2 lines are necessary, and the line that's over here, line AC, is totally unrelated to angle 3 or 4. So we're not going to focus on or think about line AC at all. So which ones must be parallel? Well, it can't be this one. This has got to be acting as the transversal for angles 3 and 4. So it must be this line here has to be parallel to that line for these to be equal. So which two lines are those? Well, this top line here is line AB, and the one right below it is line CD. So these two lines have to be parallel in order to make the conclusion that 3 is congruent to 4. Right, that's going to wrap up part 1 of section 3.2. We will look forward to the next video for part 2 to finish up section 3.2. We will talk to you later.